We will continue staying on the topic, on the same concept, and we will move further to C123 project, where we will have presented research and conclusions by Dr. Richard Heyn from SINTEF, Norway. Few words about Dr. Richard Heyn. He has obtained his PhD in organometallic chemistry from University of California, San Diego in 1992. He has worked for SINTEF since 1998, primarily emphasizing on homogeneous catalysis for carbon dioxide utilization and sustainable chemistry. He has been involved in European Public-Private Partnership SPIRE process for Planet since its inception, and occupies the advisory and programming group vice chair for circularity innovation. In addition to two other Horizon European projects, Dr. Heyn is the coordinator of the C123 project. He will continue talking today in his presentation with the same title, Results and Conclusions of the C123 project.
Okay, thank you very much. Thank you for the introduction, and thank you for the organization of this webinar so that we can talk about what has come out of the C123 project. And what I will be doing today is more along the lines of giving you an overview. I'm not going to, in this talk, go into details. I'm just going to be very sort of bird's eye view on this. There are 3 other presentations that will be given during this webinar where you will get details on certain aspects of the results from the project by the people who know a lot more about those details than I do. So this is today's reality. What I'm showing here is the flaring of natural gas from an oil well. And this isn't just a sort of a one-off situation, but it is something that exists over the entire world. What you see here on the right-hand side is a map of the gas flares throughout the world in 2012. They're throughout the entire world. Some of them are very large. And why do this happen? And it's because it's actually, for the environment, it's better to take the methane that is from these oil wells and burn it and convert it to CO2 than releasing the methane itself, since methane has a much higher climate footprint than CO2. But this is essentially just a waste of natural resources because we have all this carbon and we're not doing anything with it. And the reason all this flaring is done is because it's simply cheaper and easier to burn it than it is to convert it into something useful. And this has to do with the old realtor's phrase that the sale of a house has to do with 3 things: location, location, and location. And it's because these gas reserves that are being flared are in places where it's difficult to transport the gas. Either the gas is just a fraction of the oil, and so it's not worth collecting and shipping. Perhaps it's just not economically viable. There are lots of different reasons why companies choose to just burn the gas instead of capturing it and using it for something. So this is where the C123 project comes in. And our solution to this problem of flaring of natural gas and all the CO2 that it emits is a 2-stage process. The first stage has to do with what we refer to as the oxidative conversion of methane. This is based on a very well-known reaction called the oxidative coupling of methane. But this is different in that we are taking methane and oxygen and converting it into the C2 products, ethylene, but also we want to make an equal molar amount of carbon monoxide in this first step, because what we then want to do is we want to do a hydroformylation of that mixture. So in other words, we take the methane and the oxygen, we make ethylene and CO, and we take the ethylene and the CO and hydrogen, which we can get either from the OCOM reaction or from other sources, for example, hydrolysis, electrolysis of water, to make C3 products such as propanol, and then convert it further to other valuable C3 products such as propylene. And the idea behind this is that if we're able to do this reaction on site in these remote locations, then you have the easier transportation of these liquid C3 products and therefore you have an economic model to extract value from that natural gas instead of just burning it.
This is here, yes, these are more.
So as I mentioned, this oxidative conversion of methane is like the oxidative coupling of methane, but it's different. This has to do with the fact that the oxidative coupling of methane has been researched for years. What you see over here on the bottom left is a plot of all the different catalysts that have been screened for the oxidative coupling of methane. And you see a lot of them really do not meet the industrially relevant methane conversions and C2 selectivities that you would like to have. So essentially the entire periodic table has been investigated in these things. And despite the fact that this has been going on for years and years and years, there is no successful commercialization of this chemistry. And probably part of the reason for this is because the focus has always been on maximizing the C2 yield. And this is perhaps difficult from the chemical perspective. So what our oxidative conversion of methane step wants to do is focus on maximizing both the CO2 and the CO as products. This gives us a broader range of operating conditions, gives us a broader range of potential catalysts that we can use. It provides better atom efficiency because since you want CO as a product, you're not going to want to get rid of it or convert it to CO2, for example. And this also allows you to incorporate CO2 into products because there's a full smorgasbord of different reactions that are actually going on here over the catalyst. So just again, from a high level point of view, we have investigated a number of catalysts for this. Our partners have done also formulation studies to find optimal formulated catalysts. And so we have our preferred catalyst. There's been kinetic models of this OCOM reaction. This OCOM stage is not just the OCM reaction, but a number of other reactions, including non-catalytic reactions. And all this has been kinetically modeled. And we have therefore come from with a set of optimal reaction conditions for ethylene production. And this will be presented in a lot more detail in about an hour by my colleague Alejandro from the University of Ghent. If we go to the second step of the C213 process, hydroformylation, hydroformylation has been known for years, and it's one of the world's largest homogeneously catalyzed industrial processes. And it's important to emphasize that this is a homogeneous catalyzed process. And if you want to do this in a remote location, you probably do not want to do a homogeneous process. You would rather do a heterogeneous gas phase process because the separation processes are easier, the footprint of the reaction is smaller, and it's easier to control. Now the C3, the hydroformylation, what it does is it couples an alkene and syngas, in this case carbon monoxide and hydrogen, into an aldehyde. And the yields and selectivities of this reaction in the homogeneous system are on the order of 90 plus and 90 plus. So it's a very well investigated reaction, industrially used, high selectivities and high yields. And these catalysts are primarily organometallic rhodium catalysts. Historically, cobalt has also been used, but the rhodium catalysts give much better activities and selectivities. But again, as I said, if you're doing homogeneous chemistry, you have the separation issues that you have to, because you have to separate your catalyst from your reaction mixture. You have a solvent, etc. And also, industrially, you have very complex ligand systems to control the selectivity, because when you do hydroformylation on, say, for example, a C3 product, you can get the linear product, which is the preferred, but you can also get the branch product, which isn't preferred. So we have developed industrially very fancy phosphine ligands in order to control that selectivity, and this is something we would also like to try to avoid. So what we've been able to do in the hydroformylation bit is we actually have developed 3 new heterogeneous hydroformylation catalysts. One is based on a polyphos system, which is a conjugated organic polymer which has permanent porosity. And we also have 2 systems that are based on metal organic frameworks, which are porous materials that are made from metal oxide nodes and organic linkers. And what we've been able to do is these catalysts have been successfully tested in the gas phase hydroformylation of the ethane. So for the first time, we have shown that we can take a catalyst and we can do a gas phase hydroformylation with selectivities which rival those that are achieved from the homogeneous industrial process. And in about I guess 3 hours now, my colleague Alvaro from Johnson Matthey will give you a presentation on the details regarding all of these heterogeneous catalysts that we developed in the process. From a techno-economic perspective, we have looked at 3 different scenarios. These 5 different scenarios. These 5 scenarios are based on 3 different natural gas sources and 2 process sizes. So we have these are listed here. One of the gas sources is biogas, and the location for that envisioned biogas process is Germany. The second gas source is known as marginal gas. This is about 15% of proven gas reserves, and it's not economically viable to extract those gas reserves with state-of-the-art technology because the crude characteristics are very poor. So you have high gas and low oil reserves, and there are a number of these fields in the world, and our preferred location as a model for the process is in Russia. Our third gas source is known as associated gas, which is 25% of the proven natural gas reserves. And this is just natural gas that is found in association with oil in an oil reservoir. But again, it is flared now because these are remote locations, and it's not economically viable to capture that gas and then transport it for further use. So we have these 3 gas sources, and in the project, we have looked at 2 different process sizes, one which referred to as the modular route, which is on a 10 to 30 kiloton per year product scale. The idea being is that you would then have a containerized process that you could then put out somewhere in this remote location and do the C123 chemistry. And then we have what we refer to as the add-on route, which is a much larger scale process where the idea is that we take some of these gas reserves and we convert them, and not to a C3 product such as propanol or propanol, but we go all the way to propylene. Then it can be integrated into a petrochemical and plastic production polymerization site. And so you have to have these sorts of sizes to look at this. And so we have then process design, techno-economic analysis and life cycle analysis on all 5 of these scenarios. And these are listed here. You have scenario A, which is biogas and the modular route. Scenario B1, which is marginal gas and the modular route. Scenario B2, which is associated gas and the modular route. And then the 2 C scenarios with the different gas sources for the add-on route. And from the analyses that we've done, the scenario B2, this associated gas using a modular process located in the United States is considered to be the most promising industrial application. And this afternoon, my colleagues Mohammed and Jordi will give you a presentation in more detail on the TEA, LCA, and processes of some of these scenarios that I've described here. So when we started the C123 project in 2019, no one knew that there would be a pandemic, and no one knew that we would have this conflict in Ukraine with the weaponization of gas supplies. And so during the project, one of the questions that arose was, is this project still relevant? Because you have the increase in natural gas prices, is it still really economically viable to take this flared natural gas and actually do something with it and make a value-added product considering its price? And our conclusion, and the conclusion of the executive board on this issue, was that natural gas prices are primarily affected. Will primarily affect its large production and consumption, not these relatively smaller routes, such as the modular route, which I'm referring to. And the natural gas prices don't affect whether or not gas is flared or not. The gas is still flared even though the natural gas prices are high. So from our perspective, the C123 project and C123 concept for the conversion of these stranded natural gas reserves is still highly relevant. So what I've tried to give you is an overview of the C123 project, which offers a technical solution for the conversion of stranded natural gas into transportable C3 chemicals. We are looking at two different stages here. We're talking about an OCM route, so we have catalysts and processes for the conversion of a methane, CO2, oxygen stream into an equimolar ratio of C2 hydrocarbons, ethylene particularly, and carbon monoxide. We have developed heterogeneous catalysts for the gas phase hydroformylation of this ethylene CO mixture. And we've done process and techno-economic and life cycle assessments of 5 different scenarios for the conversion of this methane to C3 products. The project will be ending shortly. You see here the logos of all the partners, and I would like to thank you for your attention and the invitation.
Well, thank you, Dr. Heyn. We have no open questions from our online audience. Do we have any questions from the meeting room here today? We have one question.
Thank you very much for the presentation. I think it's not a question, it's just a comment. I think it's relevant for all the projects. Since all 3 projects targeted to the conversion of methane, I think that one discussion that we should start is the utilization of other sources of methane, like the biogas you mentioned, and this is very important. And the other thing is how to coordinate some activities between the projects, especially for the utilization of methane as alternative feedstock for energy and chemicals.
Okay, thank you very much. I don't have anything to add. I agree.
Yes,
so.
it was just a comment. Just a comment. I think the biogas option is something very interesting, especially as it is located in small units around Europe. So they need something in a small scale that can easily convert the methane to valuable chemicals and then transport to, let's say, the big facilities for the further treatment.
Yeah, I agree, and I will leave it to my colleagues this afternoon to explain to you why the biogas option was not our preferred scenario. I believe it has to do with the fact that we can't use all of the CO2, so then there's still a CO2 emission problem. But I don't quote me on that, and please refer to them this afternoon.
Okay, thank you.
Thank you very much for your addition. Do we have any other questions from our audience? We still have some minutes available that we can allocate. If not, we are ready to move forward.
Okay, thank you.